So let's see now some concepts and problems on two-dimensional motion. Before you move into two-dimensional motion, you should be very well familiar with motion in one dimension and all the kinematic equations, all the 5 ones that we introduced in the previous section. And also you should be very well acquainted with the vectors and how to use them, how to decompose them, how to make all the operations that we highlighted on the previous video. This vector section is not part of the exam, you will not be tested on that, but certainly you need to know it to be able to understand two-dimensional motion and also circular motion, which is in a way a motion on a plane, as we will see. Now the single most important principle, and actually all there is of difficulty in two-dimensional motion, is to realize that any two-dimensional motion, in fact any motion in more than one dimension, can be described as a motion, independent motion in each one of the components. So if we're talking about motion on a plane, and we discussed and we have horizontal and vertical velocity, and horizontal and vertical position, and horizontal and vertical acceleration, the only thing we need to do is to decompose this motion into the horizontal components and to the vertical components, and apply to each one of those the same set of equations that we derive for motion in one dimension, because at that point the motion is going to be just simply motion in a straight line, in a single line, and so we can use the equations of one-dimensional motion. So how this typically works, and we will see some examples, is that say the classical case of a cannon that's being shooting obviously a cannonball, right? And the ball leaves the cannon with a certain velocity we can call v sub 0, right? And at this point v sub 0 is a vector, we can just make the arrow if we wish, but we understand what we're talking about. Now the entire problem is just simply taking this vector, realizing that this vector, if we just zoom in, we can see that the vector goes like this. Let's say this is v0. If we draw our axis of coordinates here, we have a vertical and horizontal component, and all there is in this problem is to realize that this vector makes an angle, which is the direction with respect to the horizontal. And so by using SOHCAHTOA, we just simply need to remember that the components of velocity are going to be horizontal and vertical components, and in this case we can use, for instance, SOHCAHTOA, so that we can start with the sine of theta. It's equal to the opposite side, and so the opposite side is going to be this, and if you see, this is just simply the y component of the initial velocity, so we're going to see that that's v sub 0 y divided by, and then the hypotenuse, which is the modulus of the vector initial velocity, right? So this vector, just initial velocity. And then the same thing we can do for the cosine of theta, and in this case it's going to be the adjacent. The adjacent to the angle is, of course, the v sub 0 x component, which is the horizontal component of the motion, of the initial velocity, excuse me, on the horizontal component. And once we have this, of course, we can solve, or we can just say that the initial velocity y component is just simply the magnitude of the initial velocity times the sine of theta, and the horizontal one is v sub 0 cosine of theta. And that's all there is in here, because once we have done this, we have separated our initial velocity into vertical and horizontal components, and then we're going to treat the motion of the horizontal motion in one dimension with a one-dimensional set of equations, where our initial velocity is going to be this one, and we're going to describe the free fall motion, which is in this case the cannon. The cannon is falling because of gravity, and whenever we have gravity, we can describe that as in free fall. So we're going to use, again, it's one-dimensional motion, and it's going to be described for this with this equation for the initial velocity. We're going to find out the other information. We're going to make our set of 6 variables, and we're going to work from there. Now, important thing here, because we have defined the angle theta like that, this is the x and this is the y component, but the x and y component, but we could have defined the angle in another direction, then x and y will be sine and cosine. So what's important here is when you know SOHCAHTOA, then you can decompose in what's the horizontal and vertical components easily. And you will see in the questions of, and we will see that on chapter 2, chapter 3, excuse me, on problems on force and dynamics, that sometimes forces are applying on a plane. For instance, an object that is, take a ball that is rolling down on a plane, right? So of course the ball is rolling down because of gravity, which is there is an accelerational gravitation here, which we call g. In this particular case, what you have to realize is that it's convenient, excuse me, to describe the motion into horizontal and vertical components, but now horizontal and vertical are not just simply horizontal and vertical with respect to the entire space, but it is more convenient actually to describe the axis as horizontal, it's along the ramp, and vertical is perpendicular to the ramp. And if we use this axis, if you wish, you can call it prima, but again, there's no absolute frame of reference. You choose whichever frame of reference you wish, and then you put your axis of coordinates. And so we can choose that this is our point of view. And this is very convenient because then the ball rolling down is going to be rolling down in the x component. And so we just simply need to describe this acceleration in terms of the angle that this makes, and that angle is going to be the same one as the angle of the slope of this ramp. And so then we can decompose that acceleration into horizontal and vertical accelerations, and that's why the ball falls like this, because if there was only acceleration in this downward direction and there was no ramp, then we will see that the object will fall down. And it's just because of the presence of the ramp, that it's forcing the ball to be above the surface of the ramp, that the ball is going to be rolling down the slope. So then that's actually seen when we see that there is indeed a component of acceleration in this direction, which is the result of projecting the vertical acceleration into the direction of motion of the ramp. We will see this with more detail later, but this is just to say again, it's very important that the first thing that you realize is that you need to have SOHCAHTOA in mind to be able to solve these problems, because once you have a vector, you have to describe into horizontal, vertical components, whichever those components are, because you can decide this is my horizontal and this is my vertical, or you could decide this is my horizontal and this is my vertical, and whichever crazy system you want to come up with is going to be valid, because any reference frame, provided there is constant acceleration, which is again always the case in physics 23, is going to be valid. There is no absolute reference frame. You can choose whichever you want, and the laws of physics are going to be valid in those axes. Now, of course, there are some axes and some points of view, some frame of reference, some axes of coordinates that are more valuable than others, because make our task much more easier, and that's the whole point of this. But again, make sure that you're well familiar with SOHCAHTOA, make sure you're familiar with vector decomposition, understanding that in this case, vector v sub 0 is actually v sub 0 x and v sub 0 y, right? So what we have found is the decomposition of the y and x components, in this case horizontal and vertical, of that motion. And once we've done this, then we're going to be able to apply the equations to solve problems. So take another example. Let's say that there's an airplane, and the airplane, or just simply you're on the top of a hill, as we will see in the next problem. But you're on top of a building or of a hill, and then you drop a ball. And then you're just here, and then you drop the ball, and you throw two balls. One ball, you just let it drop, so you just let it fall, you drop it. And the other one, that's going to be a scenario, let's say 1. And then you have a second scenario where actually you're just dropping the ball with certain initial horizontal velocity. And I just want to emphasize the fact that this is a horizontal velocity, so this vector is only going to have horizontal component. So there's no vertical component of that initial velocity. And so what we expect, of course, the ball to do is just to fall somehow like this, right? And we're comparing these two scenarios and saying what's different. How long will it take for this ball to come down or for this one to come down is determined by how fast the ball is falling down. And that's determined by how much is the acceleration of this problem. So when the ball drops, why does the ball drop? Ask yourself this question. The answer, of course, is because of gravity, and we know that's because there is a result of an acceleration that we just call g, which in this is negative because it's 10 meters per square second. Sorry. So even if the initial velocity is 0 in this case, let's say v sub 0 y to represent that this is the y motion, even if the initial velocity is 0, the final velocity here is not going to be 0 because of the result of the acceleration, which again, acceleration is the result of a change in velocity over time. And of course then, final velocity is going to be given by v sub 0 at, because this is minus 10 and this is 0. We can just say that the velocity is going to be minus 10 times, this is 0, right? We just said that, minus 10 times t, where we've taken 10 instead of 9.8 because we don't want to get confused with the math. So basically this is the idea. So the first second velocity is going to be minus 10 meters per second, the second minus 20 meters per second, the third second minus 30 meters per second. So it's gaining 10 meters per second per second, right? That's what the acceleration is telling us. So by the time it drops here, depending on how long it takes, which of course depends only on the height, it's going to determine the final velocity. This is easy. We've done this in one dimension. Now let's take a look at this. And then we say, let's split the motion into components. Now if I ask you here, how long will it take to fall? First of all, let's wonder, why does it fall? Why doesn't it just go forever like that, right? Why, we will see again in chapter 3, but we know already why it's falling. Actually, it's not going upwards or any other direction, it's because there is an acceleration, and that acceleration is due to gravity. And how much is that acceleration? Well, it's the same acceleration in this case. It's just simply g, and it's also negative, right? So we had here an acceleration that goes down, and so we're also going to have an acceleration here that goes down, which is of course going to be g, which is of course going to be minus 10 meters per square second. So the acceleration in the vertical component, so maybe we can just write sub y here, right, to say that the acceleration in the vertical component is exactly the same acceleration as here. And how much is the initial velocity in this case? The vertical initial velocity is 0. We said that we throw the object horizontally. So if we have the same acceleration and we have the same initial velocity, so what's going to be the final velocity when it drops? Exactly the same. There's no other possibility because we don't have any other difference in terms of the motion vertically, right? So because the motion vertically is the result of actually the acceleration resulting from gravity, and this is exactly the same scenario in here, how long will it take to fall is determined by how high is this, and it's going to be exactly the same as this case if both have the same height, because they both will have at the end the same velocity. And velocity again is going to be v sub 0 plus at. In this case, v and v are just y velocity, right? So we could just say y velocity, and so the initial velocity is going to be 0, which is said that, because it only has horizontal components. So when I'm throwing the object horizontally, initial velocity is 0. And so I'm going to have plus, and then this is going to be minus t times 10, which of course is minus 10t, which is exactly the same thing that we obtained in this first case, right? And again, we just remember, you cannot write the subscripts here, not to get confused, to always know this is dimension. So again, we see clearly that the vertical motion, the vertical part of the motion, whether you throw it with horizontal velocity or not, or just let it drop, is exactly the same thing. The only way for this to be different is if acceleration was different, which is not because it's the result of the Earth and the Earth is the same regardless of how you throw the object, or if the initial velocity was different. When you're dropping it, you're just throwing it with 0 velocity, which is letting it fall. And when you drop it with horizontal, when you throw it, with horizontal velocity, the vertical component of the velocity is as well 0. So then you have exactly the same scenario. Both situations are exactly the same. And that's what we see, that motion can indeed be decomposed into the two components. Now, of course, how far will it reach? It's again a two-dimensional motion. We will see a horizontal component of the motion is going to be described in its own set of coordinates. But the motion is going to end the time that this reaches the ground. So, of course, how far it goes is going to be described by the x component equations. But bearing in mind that how far it's going to reach is going to be determined ultimately from the fact that the vertical motion has a limited amount of time. And so whenever it touches the ground, the motion is over. So you will find out how long it takes to touch the ground, and then use that time in your x components, in your x equations, to actually find how far it reaches horizontally. So again, this is the idea, or this is the reason why this is happening. If you had a motion where you're throwing the ball with a certain vertical component, of course the case is going to be different. But it's going to be exactly the same as if you were throwing it towards the upside, even if it's just like vertical motion, even if you're throwing with this vertical velocity, if the vertical component of this motion were the same as the vertical component of this motion. So if in both cases the vertical initial component is the same, in this case the component is the vector itself because we're moving in a line. In this case, no. So we need to find the component that is vertical and see. And if the vertical component is the same, then it's going to be exactly the same problem. So any motion that happens with a parabolic shot is going to be defined as a free fall, taking care of the vertical component, and then just horizontal motion. And of course, we will see what is the acceleration of the motion in the horizontal component. So what's the acceleration? There's no acceleration, I just need to throw it. There's nothing pushing the object forward. There's nothing acting there on the object to make it go faster. So the acceleration is going to be 0. So the initial velocity, of course, is going to be given by the component in the x direction, which in this case, if we take the case of just simply horizontal throw, that's going to be v sub 0. And if we say that it has an angle, then we have to project that into the horizontal component and find out the velocity. And then we have simply just a case where we have horizontal motion with no acceleration. Now, acceleration is the rate of change of horizontal velocity. In this case, horizontal acceleration is the rate of change of velocity in the horizontal component. If you have no acceleration in the horizontal component, it means that there is no rate, or the rate of change is 0, meaning it's not changing. So what's going to be the final velocity when it touches the ground for the horizontal component? Well, the same as the initial, because there is no acceleration, there is no change in velocity. That's by definition here, right? And so we're going to see that these examples are pretty simple as soon as we're capable of splitting the motion, so to speak, into vertical and horizontal components. This is the case for objects falling on Earth, which is the case of a cannonball, or you kicking a ball, or just dropping an object or something like that. But it also happens in the case of motion on a plane. But in that case, of course, acceleration is going to be split into the horizontal components, and then there's no gravity. So most likely acceleration in that motion is going to be just simply 0. So let's see more examples more precisely from the discussion problems now. So let's solve problem 1 from the discussion section. And in this case, we have a projectile being fired from the top of a cliff, right? So let's make a small diagram here. We're just throwing, let's imagine this again, a cannon, and it's also shooting a ball, a cannonball or something like that, a projectile, and it's fired horizontally with a speed of 30 meters per second. So we can draw in our diagram initial velocity. We draw it horizontally because it says it's fired horizontally with a speed of 30 meters per second. So we can just say that the horizontal velocity is 30 meters per second. Now, let's write just simply 30 meters per second, right? So this is actually the magnitude of that vector. But the direction, we know it because it tells us. So then immediately we just know that the velocity components are 30 meters per second in the horizontal and 0 meters per second in the vertical, because the motion only has horizontal component, right? So remember, this is going to be the horizontal component, and this is going to be the vertical component. So we can just say 0. So we can say y0 or 0y, whichever way you want. So the subscripts here are referring to the coordinate you're considering, and of course the subscript not, we know we just use it to identify or signal that we're using initial condition of the problem. And then they tell us that the cliff is 80 meters high. So now we have an idea that this is 80 meters high. So what information is being given with that? That's actually the initial position in the vertical component. So whenever you don't have information about the horizontal position, typically in this sort of problems, or even if it's a free fall or something like that, well, not in the case of a free fall, where you're throwing an object upwards and then falling down, you can, in many instances, take position equal to the initial position to be 0. Just bear that in mind, because if the object falls to negative positions, if there's the floor, then you made a mistake, but if not, then you're going to be fine. You just need to remember, if you either find this as 0, the ball falling down is going to have negative position. So that's a matter of how you define your axis of coordinates, right? And so the question is going to be, how long will it take to strike the level ground at the base of the cliff? Before we go for this, let's make the first thing that we need to do, which is, of course, identify. We're going to have the horizontal motion, and we're going to have as well the vertical part of the motion. And so, let's say something like this. Okay, and so what do we have? We can start putting the information that we have. So do we know the first question, of course, is about how long will it take to strike the level ground. So we want to know when it drops, time here. When is the time happening here, right? And this is, of course, the ground level. So just see what's the time there. So we start identifying the information that we have. Do we know the final position? Actually, we don't. We don't know how far it's going to drop. We'll figure it out during the problem. Do we know the initial position? Well, in this case, it's one of those cases where you can take the initial position to be 0. If you don't, then just instead of solving for x, solve for delta x, which is the total displacement, which again is exactly what you want to know, because you're throwing from the beginning. So choose your beginning to be 0. Very convenient. There's nothing wrong with that. Then we're going to have the final velocity. Do we know the final velocity into the horizontal component? Let's talk about that in a second. And we're going to ask what's the initial horizontal component of the velocity. So let's think about this. Do we know the horizontal component of the velocity? Well, it tells us it's 30 meters per second horizontal. So as we identify already, this is going to be 30 meters per second. And then I have acceleration in the x component. Now we put x component to distinguish. Is this being accelerated by anything? Well, it doesn't have, you will see that accelerations are always the result of forces. So a force is typically, your car has an engine, you have legs, and then your muscles use the energy that you eat and all those things, right? So there always needs to be some source of the motion. But a cannonball is inert. It just follows whatever impulse was given by the cannon. So in horizontal motion in here, there is no acceleration. So we know this. We just don't have to figure out, because the motion is not accelerated, it's going to be 0. And the motion is going to have 0 acceleration horizontally, constant, because all our problems always have the same acceleration for all the problem, and so we're going to know immediately that if there is 0 acceleration and initial velocity is 30, how much is going to be the final velocity? Well, the final velocity is always going to be the same as the initial, because there's nothing slowing down the object. The only reason why in real world we see the objects actually slowing down is because there is friction from the air, but that's a source, that's a force that is acting against the motion, right? If you go out in a windy day, you feel the wind hitting you, right? But we have removed in our scenario all the wind, all the atmosphere. This is an ideal scenario so far. So because there's no air, there's no friction, there's no opposing force, there's not going to be any acceleration. We will see again more on this in chapter 2. Acceleration is going to be 0. And so if acceleration is 0, that's the definition of acceleration, is the rate of change of velocity in time. But if there's no rate of change of velocity in time, it means the velocity is the same always. And so we immediately know that this is, of course, 30 meters per second. And finally, the time. Do we know the time? Well, this is actually what it's asking. And time is the same for both motions, because, of course, time is the same for the entire experience, right? So we don't know that time, but that time we can figure it out if we know. We'll see now that we're actually going to figure it out based on this. So let's go for it. So let's see. What do we know about the vertical motion? Well, for the vertical motion, we have the final position and initial position. Do we know the initial position? Well, it's given by the height. It's just 80 meters, right? So we just write 80 meters. Do we know the final position? Well, we do, because it is asking us the time when it touches the ground. And how much is that? That's 0. So this is the information that we're reading from the wording of the problem. Now, we need the final velocity and we need the initial component in the vertical also direction. So what is the initial component of the vertical direction? Well, it is thrown or is shot with 30 meters per second horizontally. So what is the initial component for the vertical motion? We just saw is 0. And now what is the acceleration? Well, this is a vertical motion, so we know the acceleration can be 10, negative 10, because it's going downwards. And what's the final time? Well, we don't know. That's actually what's being asked in the problem, right? We want to know how long it takes to reach 0 position. Now, what about the velocity? Do we know anything in the vertical velocity? Well, you might be tempted to say, well, it's 0, it's also 0 here, but don't make that mistake. Here is the same because acceleration is 0, but this is an object that's being accelerated. So the velocity is not going to be 0. So 2 problems. Do distinguish between the conditions where you're analyzing the horizontal and the vertical parts of the motion, but also do not forget that this doesn't come out of nowhere. It comes from applying the definition of acceleration. Acceleration is the rate of change of velocity. When there is no rate of change, it means there is no change. If there is no change, velocity is the same. When there is a rate of change, then velocity is not going to be the same. So we know immediate velocity is not 0, even if you're dropping the object. And this is exactly what's happening here. This motion is exactly the same as if I drop an object, because again, the horizontal component and vertical components are completely or are independent in this treatment. Of course, they're not independent because time is the same in both cases, right? So this time is exactly the same as this time. This is the only thing that they share, because it's the same event, so the time needs to be the same for both descriptions. But this is exactly the same thing as a free fall. And as you know, free fall velocity when the object reaches the ground is never 0. And if you ever have questions about this, just imagine yourself standing under a window and someone is throwing a can of paint or a gallon of water or a piano, if you wish to make it like more dramatic, right? Cartoonish, so to speak. So will you stand under the window? Of course not. It would kill you, obviously, but it would just destroy you, right? It's painful. So why do you stand away? Because it's coming with a certain velocity. And why you see that? Because if you enter in a room and there is a table, the table is sitting there, it's not moving, what's the velocity? 0. You're not scared about the table sitting on the room, but certainly you will be scared about someone throwing a table out of a window, right? And why is that? Because the object is coming with velocity. So that's the same problem with a car. You're not concerned if the car is parked, but you're certainly concerned if you're crossing and the car is coming to you, because the car is coming with velocity. And so intuitively, you know already, I'm not going to stand in the middle of the car, I'm not going to stand behind or underneath a window where someone is throwing something. That's because the object is falling with velocity. So of course this is not going to be 0. It's never 0 when it reaches the ground. So once we have the set, let's make it more nice and let's solve for time and let's see how to do that. Before we go with the actual answer of how long will it take to actually reach the ground, let's make this more precisely, more technically. So if we have any vector at the beginning, we need to decompose it into the components. In this case, it's trivial because we just said it goes with horizontal. But let's see exactly how we would do it in any general case. So let's say that the velocity is thrown, this is your initial velocity, which again is a vector, and so it's given by the magnitude, which is the modulus, and an angle theta that we can define with respect to the horizontal line. So what are our components of the vector? Well, we just saw it a second ago. The components are going to be v sub 0x, v sub 0y, and we know from SOHCAHTOA that this component is v sub 0y, which is given by sine of theta v sub 0 times sine of theta. And then we have here, we just saw it before, you can go back on the video and see that this is v sub 0 cosine of theta. SOHCAHTOA, so K is cosine is equal to adjacent divided by hypotenuse. This is a hypotenuse, this is the adjacent. So adjacent is equal to hypotenuse times cosine. Sine is so it's sine equals opposite of hypotenuse. Hypotenuse is dividing by multiplying. Here we have it. And now immediately see, if the object is with a velocity, as in this case, that it is horizontal, if it's purely horizontal, then how much is theta? Well, it just goes all the way down. So it's aligned with the x-axis. So how much is theta? Is 0. And then immediately you know that the cosine of 0 it's 1. Well, and and sine of 0 is 0, right? So how much is this? This is going to be v sub 0 times 1. This is going to be v sub 0 times 0. Whatever is multiplying 0 is going to be 0. So of course it's going to be then that v sub 0, and this is still a vector, it's equal to v sub 0 times 1, v sub 0 times 0, and this is of course 0. So that's just simply v sub 0 modulus comma 0. So this is exactly what we observed here. If the angle is anything else, then you replace the angle and you find. And what about the other extreme scenario when this is completely vertical? When it's completely vertical, what we find is that the motion in the vertical component, well, the cosine of 90 degrees is of course 90, which is of course p half if you make it in radians. So this is going to be 0, and the sine of 90 is of course degrees, right? Is of course 1. So we have actually the opposite scenario. So the entire velocity is given by v sub 0 times 0. This is the x component, which is 0, and then you're going to have v sub 0 times 1, which is just purely v sub 0. So again, as the definition, entire motion is going vertically. In this case, the entire motion is going horizontally. So mathematically, we see everything in between is given by actually plugging the number that we need the angle to be, right? If it's 30, then that's 30. If it's 60, 90, 75, well 90 is this case, 75, whatever you like, that's going to be plugging and actually describing. So this is how we exactly do that. Just bear in mind, sometimes your calculators will have two functions. You can decide that you're plugging the angles in radians, or you can decide that you're plugging in degrees. So make sure that you're familiar with your calculator for the exam and actually how to use your calculator in general. When you are inputting degrees, the angles in degrees, you have to make sure that your option is selected that way, because 0 degrees is the same as 0 radians, but 90 degrees is not the same as 90 radians. So make sure that you have set your calculator to have the right settings. So read the manual or search on Google or YouTube or whatever, and figure it out for your calculator if you're actually going to need a calculator for your exam or your homework or something, because otherwise it's going to be impossible. Again, the idea here, we have a velocity with a certain inclination or certain angle. That's what we call the direction. It has a magnitude, which is what we call the speed, right? The magnitude of a vector is the speed. In the dimensional motion, it just matches. So then we have a certain speed or magnitude of vector, and we have a direction. We can decompose the vector. And once we have the x and y components, then we can plug them in our set. Let's go back to the original problem now. So now we're going to try to solve the question of when is touching the ground, right? Which is part A of our problem. Now we could try to do it with a vertical component, or we could try to do it with horizontal. If you try to do it with a horizontal, you're going to see that it's actually impossible, because you don't have any information of how much time it takes to actually do the motion. So there's no equation that's going to give you any information of how long it's going to take to reach that position. You don't have a spatial information, you don't have time information. You're missing two, not one. So you can actually not use the horizontal motion, you have to use the vertical. And it makes sense because at the end of the day, how far it reaches depends on how long it takes to touch the ground. And touching the ground, again, is completely independent from advancing horizontally, vertical and horizontal motion. So we need to use actually the vertical component of the motion. And then we have our equations where we have, we're being asked about the time, right? And we are missing, and we know, time when y is equal to 0, right? We could write y equals to 0 if you want, right? And so when it touches the ground, when the final position is 0, what's the time? What are you missing here? Well, you're actually missing information on the time. You're also which is being asked if we use the notation or the way of speaking that we used in the previous section on one-dimensional motion. But what we're actually missing is the final velocity. So final velocity is missing. So we need to use the equation that has initial position available, that has spatial information available, that has acceleration available, that has time also included because we're going to solve for time, that has velocity. We're looking for the equation that it's missing v sub y. And that equation, of course, is going to be just the equation for y equals to y sub naught plus v sub 0 t plus at squared divided by 2. Right? Let's not forget that this is sub y, so you can add the sub y subscript there not to mix if you confuse them. So be careful with subscripts and superscripts until at least you are comfortable with these equations, right? And so we can replace, just then substitute the information that we have. So do we know the final position? The final position is 0. Do we know the initial position? The initial position was 80. Do we know the initial component of the velocity in the y, or the initial velocity, the y component of the initial velocity? Well, that was 0. So we're going to have 0 here. Do we know the time? No, that's what actually we're trying to find. And do we know the final acceleration? Well, or the acceleration, excuse me. Well, that's going to just be minus 10 because it's vertical motion. And do we know the time? So the time is what we're trying to solve. And then we divide this by times 2. So that we can go forward, and then we see that with 0, it's equal to 80. That goes to 0, right? And then plus, and that's minus. So that's going to be minus 10 squared divided by 2, which is, of course, 80 minus 10 divided by 2 is 5, and there's a minus, so that's going to be minus 5t squared. And so, of course, we can see that 5t squared, it's equal to 80, and finally, t squared, it's 80 divided by 5, and that's going to be 16, right? And so we have the t, it's equal to plus minus square root of 16, which is plus minus 4. We discussed this in the previous instance, because we have a quadratic equation, that's an equation with degree 2, we're going to have two solutions. The two solutions are given by the plus minus before the square root. If you're using the quadratic form, remember that any, let's say, ax squared plus bx plus c equals 0, you can solve for x, just remembering that it's equal to minus b plus minus b squared minus 4ac, and all of this divided by 2 times a, where a are the coefficients multiplying x squared, b is the first degree, and c is the 0th degree, basically the one that doesn't have anything attached. And in this case, of course, if we compare with this, x squared for us is t squared is a, so a is the only component, but b is, of course, 0 because there's nothing multiplying t. So you could use that equation, just simply b is 0, c is going to be 80, and a is going to be minus 5. Right? So then we find the two signs. Now, of course, again, remember, mathematics is the tool that we're using to develop the information, but at the end of the day, it needs to be a physical description, meaning it needs to be a description of the real world. Now, we have no idea, we have two solutions, plus and minus, but there's no such a thing as negative time. Time always goes forward. You see then principle of thermodynamics that kind of explains why the arrow of time is always seems to be pointing always forward. So basically, we know it cannot be a negative solution. We only can use the positive solution because it doesn't make sense to say it takes minus 4 seconds. It means it's going back in time. That doesn't make sense in this scenario. So time here represents 4 seconds. That's basically saying it takes 4 seconds for the object to fall. If you analyze the same, but forget about the horizontal velocity and say how long it takes for an object in Earth to fall, to drop 80 meters, you're going to find that that's 4 seconds. And that's regardless, again, of the object, because there's no mass in here. That's the beauty of the universality of these equations of motion. So we found the time. Let's see what else we can do with this information. Now, part B is asking how far from the foot of the hill is going to reach the ball. Now, of course, that's a question of how far, so that's a question in horizontal motion. Now, we said we couldn't figure out any information on horizontal motion because we're missing 2 pieces of information, not just one, and asking for another. We're actually missing 2. So we can not use this equation, but now we found the information that was missing, which is this, how long it takes. So now I can use my equations where the time now is going to be 4 seconds. And the question is how far is it going to reach? Basically, what's the final position at time equals 4 seconds. So now we can use any equation, but of course it makes sense, for instance, to use the simple equation that we just used before, which says that the position is equal to initial position plus initial position times time. We can just be careful with the notation. Let's add the subscripts. And so we can go back to our set of data and see. We know what's the initial position. Well, we can take that to be 0. Do we know, excuse me, 0, just 1 0, no 0 sub 0. How fast does it go in the initial velocity? Well, the initial velocity is 30 meters per second. So we have 30 times t. How much is t? 4 seconds. So we write 4 seconds. Plus, what's the acceleration in the x component? 0. So we just write 0 times 4 squared divided by 2. Now, of course, this goes to 0, right? And so we find that the position is 30 times 4, which is 120 meters. So how far will it reach the object? 120 meters from the foot of the hill, because it took 4 seconds. If this was taller, the time to drop will be higher. And intuitively, we understand that the object will reach farther away from the foot of the hill. That is because this time is going to be not 4, but something else. But that's the only thing that changes in this equation. Notice that the only thing that we're changing in that case is time. And that time ultimately comes determined by the fact of the object touching the ground, which is based on the vertical motion and the vertical component of the motion. So that's the kind of the connection that we have between these two motions, or this two-dimensional motion, right? Between the horizontal and vertical description. It comes through the time, right? But there's no other connection here. They're purely independent from each other. So we found how far it is. Let's do the last part of this problem. And so the last part is asking us what's the final velocity when it touches the ground. If I ask you what's the final velocity in the x component, we immediately know there is no acceleration, so final velocity is the same as the initial, so we could figure it out. Actually, you could just say, what's the final component on x? Well, you just say is the initial x plus a sub x times t. Now, we know the time, we know the initial velocity. How much is this acceleration? 0. So how much is this going to be? v0x. So for no acceleration, of course, final velocity is the same as the initial. So what's going to be the final velocity in the x component? Well, just simply the same as the initial, which of course we can just say Vx is equal to 30 meters per second, which is what we just identified previously theoretically, or based on the concept of acceleration. It's just trivial. This equation actually was derived, as we saw in the lectures, from this concept, from the definition of acceleration, right? And assuming acceleration is constant and is initially 0, it's always 0. Therefore, this equation applies well, and we know the final velocity is the same as the initial. But what about the vertical component of the velocity? Well, that's going to be also Vyx plus at, a sub y. In this case, excuse me, that's going to be y0, not yx. So in this case, the final velocity we can replace is, what's the initial velocity? Well, the initial velocity is 0, because it only has a horizontal component, which is so over here. And what is the acceleration in this case? Well, acceleration in this case is minus 10. So we need to write minus 10. And how long does it take to do the motion? Well, it takes 4 seconds. So we just figured it out in the previous example, right? So what's going to be this? That's going to be 0 minus 40, which of course is minus 40 meters per second. Now, we found the final velocity, right? So we have that the x component is plus 30. That means it's going to keep going with 30 meters per second. And the vertical component is minus 40, which is going downwards. Let's draw that in the form of a vector and answer this with a little bit more of detail. So now let's see. We have said that the horizontal final velocity is 30 meters per second, and the vertical motion has a minus 40 meters per second. So if we just want to plot the thing, let's make our x and y components, right? And so we know this x is going to be about 30. Let's say that this is 1, 2, and 3. Actually, no, let's not do that. Let's do a little bit less, so 1, about 2, 3, 4, okay, nice. So now we have, oh, actually, anyway, yeah, 1, 2, 3, 4, okay. And so we can paint. The first one is 30x, so this is the vector that we have, right? This is the vector of Vx, if you wish. And then you have the x, that's the x component, right? You need to go 30 towards the right. But what about the vertical? You have to go 40 down. So if this is minus 10, this is minus 20, this is minus 30, then this is minus 40, so you need to go minus 40 down. So that's about here. So that's going to be the Vy, right? So how much is the final velocity? Well, final velocity is actually given by x and y components. So we can just simply say this is 30 minus 40, or we can realize that the final velocity is actually this vector, and so that's going to be given by the magnitude of v is the components squared, which is 30 squared plus minus 40 squared, and that's going to be the square root of 900 plus the square root of 1600, which is the square root of 2500, which is just 50 meters per second. So usually in these problems, if they're asking about the speed at the end, do not forget that the object has horizontal and vertical components. So do not simply answer with the vertical component. You have to consider the entire motion. So either you answer with this vector, or if it's asking about the magnitude, once you have identified both components, remember what's the definition of the magnitude and find out. And we could actually find out also the theta, so we could just do that the tangent of theta is of course the vertical component, right, which is Vy divided by Vx, which in this case will be minus 40 divided by 30. And then from here we could figure out an angle, which I haven't calculated, but you could figure it out. And so you would have the complete description because you would have the direction and you would also have the magnitude. If you do this number is going to be negative, so the tangent, of course, is going to be a number that is going to be a tangent of r tangent, so it's the inverse of the tangent, is going to be negative. So remember, whenever you're in the first quadrant, if you imagine a circle, right, for theta, and theta goes like this, whenever in the first quadrant you're going to have positive sine and cosine. In here you're going to have positive sine but negative cosine. In here you're going to have negative cosine and negative sine, and in here you would have negative sine but positive cosine, because in a way these vertical components give you the sine, this one is the cosine, right, the sine of the cosine. So those are sanity checks to make in here. So these ones are going to be negative tangents, these ones are going to be positive tangents. Things to remember, those not necessarily for the, necessary for the exam. You're going to have a calculator, just plug the numbers. Again, just remember that if you have set your calculator in degrees, the answer of the arc tangent is going to be in degrees. If you have it in radians, it's going to be in radians. So whenever you see the problem, if you have it set in radians and the answer is in degrees, either you reset your calculators to degrees, or you take radians and convert into degrees, and conversely, if it's the set in degrees and it's asking radians, get your degrees converted into radians. But important, the question was what's the velocity when it touches the ground? The velocity is going to be 50 meters per second. It's not minus 40, it's not 30. It's 30 in the x component, minus 40 in the vertical component, which of course makes sense, the object is falling down. We wouldn't expect the vertical component to be positive. But we need to consider both to actually calculate the magnitude, because that's the actual velocity of the object. The object was with 30 meters per second initial velocity, and it has still that 30 meters per second in the x component. But because it has fallen, it has accelerated, it has gained vertical velocity, and that vertical velocity we see here, overall, the velocity of the object increases, and that's what we see over here. Now, before we actually go for that, we said we didn't answer. If you make this division and you actually apply the arc tangent, you're going to find that the angle is going to be minus 53 degrees, right? So, what does it mean minus 53? If we define this as the direction of the positive theta, meaning theta goes from 0 to 90 to 180 to 270 to 360, which of course is the same, or we can do it in radians, right? Or we could do it in radians, and so we have 0 radians, we have half pi, we have pi, we have 3 pi halves, and we have 2 pi, which again is the same as 0, right? Which is 2 pi, 4 pi, 6 pi, etc., right? We're doing 2 pi's. That's because we're counting in the positive direction. If you have a negative angle, then you have to do the opposite. You either do two things. When you have a minus 53 degrees, right, you can add 360, and then you end up with a positive number, which is going to be 307 degrees, right? So theta is actually 307 degrees, which is going to go 90, 180, 270, and 37 more to actually reach 380. So it's going to be something like this. Or you just simply count clockwise, right? So this is counterclockwise. You could go clockwise and do minus 53 degrees, which of course is going to end up finding the same angle. So that's going to be the angle that we have in here. So there's two ways of seeing, which of course makes sense because it needs to have horizontal component but also vertical component. So the angle was looking like this. So theta is of course negative if you count like this. If it's positive and you have if you want to go in the positive direction, then add 360 and make the number positive, you're going to find is 307. Every 360, we just repeat the cycle. So every time we can subtract or add 360 to make sure that every angle that we have is between 0 and 360. Small trick here, but anyway, this is negative 53 or 307. Both are the same case. We found both the direction and the magnitude of the vector. Now, yes, let's go for some more problems. So let's try problem number 3. It says that a baseball is thrown with the initial velocity of 100 meters per second at an angle of 30 degrees. So we can start seeing and drawing information, and it's 30 degrees above the horizontal. How far from the throwing point will the baseball attain its original level, right? So we have someone throwing a ball, and it's going 30 degrees above the horizontal at 100 meters per second, right? That's the initial velocity. Right, so we have this scenario, and we're being asked at what point in the horizontal component the ball basically will reach the same height, which is, if we assume this to be the ground, will be 0. If we assume to be 10 meters, 10 meters, right? That's your choice. So let's first identify all the information and again split our motion into the two components. The first thing we need to do, of course, is, as always, split vertical component of velocity into, right, the initial velocity into the x and y components. So in this case, so katoa, vertical component is the sine, horizontal component is the cosine, because it's going above the horizontal 30 degrees, both are going to be positive. So actually v sub 0 is going to be 100 times cosine of 30 and 100 times sine of 30. If it was 30 below, there's two options. You just make your triangle and see 30, still the sine would be the vertical and the cosine the horizontal, but if it was below, we will know the velocity in the vertical component is negative, so we would have to add a minus here to be careful, or just remember that the angle is defined as below, so it's minus 30, or 360 plus minus 30, which is 330. So we will go 330 degrees or minus 30. If we just keep the 30, it's fine, just do your diagram and remember to correct for the sign based on the physical situation that you're actually considering. So cosine of 30 is about 0.86. The sine of 30 is 1/2, so 0.5. The cosine of 60, which is the complementary, is just the opposite, right? Sine is going to be 0.86, cosine is going to be 1/2. So then we have that, and then we can just write 100 times 86 is going to be 86 meters, and this is going to be just simply 50 meters per second. So if you actually make the square of these two, you're going to find that this is indeed about 100. It's an approximation, it's not going to be exactly 100, but approximately it's going to be 100. The square of this plus the square of this, square root of that, it's the initial velocity. So we have the initial velocity in the two components. We can bring our information to our set of equations. So the v sub 0x and the v sub 0y. So let's go to the horizontal motion. What's the final position? We don't know. That's actually what's being asked. What's the initial position? Well, we can just take that to be 0. What's the final velocity? The final velocity we don't know. What's the initial velocity? The initial velocity is 86. What's the acceleration? Well, what's the acceleration in any horizontal motion? Well, there is no acceleration, 0. So then we can go back and say, oh yeah, we actually knew this. This is 86, right? And then what's the final time? We don't know. Let's go to the vertical motion. Final position, where we're actually wondering what is going to happen when this is 0, right? What is the initial position? 0. Let's take it 0. What's the initial velocity? Well, the final velocity, we don't know. What's the initial velocity? Well, that's 50. So we can just write simply 50. What's the acceleration? Minus 10 is gravity. And what's the time? We don't know. Note here, vertical motion, we said that in free fall, is always symmetric. So if you throw an object upwards with certain initial velocity, v sub 0, we can call it v sub 0y. When the object goes up, reaches a maximum point, where v sub y is 0, and then it comes down. And it comes down to reach the same point, and at that point, your velocity is going to be minus v sub 0y. Why? Because velocity is v sub 0 plus at. If you have minus 10 and this is t, you have v sub 0 and then you have b. So by the time this reaches 0, velocity, then this is 0, and then you find the time for that, which is simply v sub 0 divided by 10. So if it's 30 meters per second, that's going to be 3 seconds. Why? It's losing 10 meters per second first, so it goes from 30 to 20, 20 to 10, 10 to 0. And then what's happening? Think from the point of view of I drop an object. How fast does an object gain velocity? Well, it gains velocity at the rate of acceleration. And how much is that? 10 meters per second. So the first second after reaching the maximum is going to be minus 10 meters per second. The second second, minus 20. The third second, minus 30. So indeed, the object is symmetric. So because we're asking what's the velocity at the end, we can conceptually just say simply, well, I know this solution, this is just going to be the same, but negative. But we're not going to do that for the time being. Let's just keep going with this information. So we're asking, when does it reach the same level? Which is another way of saying what is time when y is equal to y0, and both we can choose them to be 0. So how do we find time? Well, a good option is just to use this equation. Again, you can choose whichever equation it's convenient to you and you have available. You can just use this equation. Now we identify things. Y is 0, is the same height. Y sub 0 is... Actually, it doesn't really matter, you know, because if you were taking just y to be whatever, let's do it the most generic way. You can take 0 and this becomes trivial, but let's just pretend that we don't even choose this to be 0. We just say y is equal to y sub 0, and we don't know how much is that. Let's keep y. Y sub 0, then initial velocity. How much is the initial velocity? It's 50, and it's positive. So 50 times time, right? And then what comes next? Well, you have plus acceleration, minus 10, times t squared. That's what we're trying to find, divided by 2. So we want to solve for t, but just notice, I can take this one subtracting here and then say y minus y sub 0 is equal to 50t minus 5t squared, right? Minus 10 divided by 2 minus 5. But how much is y? Y is equal to y sub 0. So what's going to happen with this? This goes to 0, right? So then I get the same thing, 50t minus 5t squared. This is the beauty of actually talking about displacement. If there's no displacement, we don't even need to have information. Provided they're the same, that's kind of adding information. If you're more comfortable, just say that they're both 0, and that just solves the problem. If you don't mind doing it more like symbolically, then you just solve for any scenario. In any case, if you write 3 here and 3 here, 3 is going to subtract, it's going to cancel anyway, so you can write whichever number you like here. Put 0 if you're more comfortable, just to make it the most general case. And now we have this equation. And now this is a quadratic equation. Remember, we can just write a quadratic equation. Let's write it in t's. So we say at squared plus bt plus c, it's equal to 0. How much is t? Well, t it's equal to minus b plus minus b squared minus 4ac divided by 2a. So we can just replace in our equation, and then we see how much is b. B is whichever number is multiplying the square. So, excuse me, a is whichever number is multiplying the t squared, so that's 5. But it's not 5, it's minus 5, because everything is positive. So a is minus 5. Watch out for the sign. How much is b? Whatever is multiplying the t. So b is 50. And how much is c? Whatever is not multiplying the t. What's not multiplying the t? Nothing. And in math, we call that 0. So then we can just replace the numbers and write minus 50 plus minus 50 squared, which is 2500. Well, we can just keep the 50 squared for the time being. So 50 squared, excuse me, minus 4ac. So 4 times minus 5, 4 minus 5, include the sign, times c, which is 0, which of course is going to go to 0. And this is divided by 2a, which of course it's equal to minus 50, and a is going to be 2 times minus 5, right? So we finally have minus 50 plus minus a square root of 2500 minus 0, which is 2500, which is to say it's just 50 squared, so square and square cancel, but anyway. And then divided by 2 times that, which is minus 10. So what we have is minus 50 plus minus 50 divided by minus 10. And wait a second and erase and rewrite this so we observe something which is very interesting. So we have minus 50 plus minus 50 plus divided by minus 10. And because I have a plus minus, I'm going to have two solutions. And of course, I expect to have two solutions because it was a quadratic equation. So quadratic equations have two solutions. Let's go when we take the plus. Minus 50 plus 50, right? Minus 50 plus 50 divided by minus 10. Minus 50 plus 50 is 0, so 0 divided by minus 10. This is 0. 0 what? 0 seconds. We're talking about time. What about minus? Minus 50 minus 50. Minus 50 minus 50 divided by minus 10. Minus 50 minus 50 is minus 100 divided by minus 10, which is, or negative 10, whichever you want to say, which is of course positive 10. So it takes 10 seconds. And now we see the y. At what times does the object, is the object at the initial position? Well, at two times. When it ends the motion in this case, because it reaches the same point, but also the beginning. So this is exactly what this is telling you. The time 0, object was at the height that we chose. Of course, because we imposed that as an initial condition. So it cannot be otherwise. This is a good time to say, oh, sanity check, this makes sense. What's the other solution? 10 seconds. So how long it took? 10 seconds. This is actually the answer that we're interested in. Because if you plug on your equations for horizontal motion, which is actually the question, what's the position when time is equal to the solutions? If you put time 0, of course, x is going to be x0. By definition, that's 0. Just put it in the equation and figure it out yourself. You can see that in 0 seconds. Well, 1 second. And then 10 seconds. So we're going to see what's the solution. Well, we know that x sub 0 plus v sub 0 t x plus a sub x t squared divided by 2. Let's use the information we have and replace. So what's the final position? That's what we're trying to figure out. What's the initial position? We can take it to be 0. What's the initial velocity in the x component? That's 86. What's the time? That's 10. What's the acceleration? 0. What's the time? 10 squared and divided by 2. Again, there's no acceleration in horizontal motion. This is very important. This is critical. Otherwise, you will never solve anything, right? So this, of course, is going to be all going down to 0. So what's x? X is just simply 86 times 10, so 860 meters. So what's the final answer to the question? How far it reaches? How far it reaches when it reaches the same height? Well, 860 meters. So let's do one more problem. Now we're asking problem 4 in the discussion. It says a ball is thrown from the top of one building towards a wall, building 50 meters away. The initial velocity of the ball is 20 meters per second and direction is 40 degrees above the horizontal. How far above or below its original level will the ball strike the opposite wall? So we have to imagine that there is a building, and here there is a large enough wall, of course. Otherwise, if it avoids the wall, end of the story. And then the ball is thrown from the top of one building towards the other one, and we know that this is 50 meters away, and we know the initial velocity of the ball is 20 meters per second, and in the direction is 40 degrees above the horizontal. So we have the horizontal, we're going to put theta equal to 40 degrees, and we're going to have the magnitude of that velocity to be 20 meters per second. So we don't know how high is this building, we don't know how tall enough, of course we're going to assume because it needs to hit. And we're asking, once we throw this ball, right, this ball is going to go like, let me just lower the building so I can write that. But basically the idea is the velocity is going to go that way, right? So this is going to go like and it's going to hit somewhere. And we're asking, hey, where is this thing hitting, right? Actually, we are interested in how far below. So we're going to measure with respect to the building itself. So we're going to measure this delta y, which is y minus y sub 0, excuse me, and y, or negative delta y. We will see that in a second. So let's just move here and say, let's erase that and write this is final position, this is the initial position, right? If we assume the building is as tall as that. So let's see, let's start identifying information. Of course, the first thing we need to know is SOHCAHTOA, and again, we can just describe our motion. In this case, with the vector, it's going to be the cosine is going to give you the x, the sine is going to give you the y, so the initial vector velocity can just be written as 20 times cosine of 40 degrees and 20 times sine of 40 degrees. So if we make these numbers, we can see, so these are 15.3 meters per second, and the y component is actually 12.9 meters per second, again approximately, right? So we can take that information and start filling our information, let's say, parameters, right? So what's the final position in this horizontal motion? In this particular example, we've been given the final position because we're asking what's going to happen at 50. So we can just write it right here, 50. And what's the initial position? Well, let's take it at 0. Let's write our axis of coordinate here, and so this is x and this is y, and then we take this to be 0, right? Is the origin of coordinates. Okay, so what's the final velocity? Well, we don't know that. Actually, we do. You should know by now immediately. When you see this motion, what's going to happen with this. But anyway, what's the initial velocity? 15.3 meters per second. And what is the acceleration? Well, the acceleration is 0. So then we can go back. What was the final velocity? The final velocity is going to be the same because this motion is not being accelerated. And what's the time? Well, we actually don't know that. So let's go to the vertical motion. Well, what is the initial position? We don't know. Actually, they have not told us. And what is the, what's the initial position? We don't know. What's the final position? Actually, that's what we're kind of trying to find out. So what's the final velocity? We don't know. We should be able to figure it out at some point. What's the initial velocity? Well, the initial velocity is plus 12.9 meters per second. That comes from here. What's the acceleration? It's minus 10. And what's the time? We don't know. So actually we have very little information for the y component, for the vertical part of the motion. So then that's kind of giving us a clue that the first thing we need to have to find is how much information we get from the horizontal. In fact, the only thing that we can use to connect both, which is this time. So from horizontal we're going to have to find time, which is the only thing missing, so we can plug time and figure out this when we're missing that, right? So let's see. First let's go with the original time. We're asking what's going to happen. So we're going to start with the horizontal motion, right? So in the horizontal motion, we're going to say that x is equal x0 plus v sub 0 t plus at squared divided by 2. For instance, you could use any of the other equations, right? That has time, because you're going to be solving for time and you have all the other information, so you can choose freely whichever you want to choose. This is nice because in horizontal motion, acceleration is 0. So the final position is going to be 50, the initial position is 0, the initial velocity is 15.3. The time we don't know, we're trying to find. The acceleration is 0, time we don't know. This goes obviously to 0. So 50 is equal to 15.3 times t, and this is 50. So time is just simply 50 divided by 15.3, which is going to be equal to 3.3, about that. So we have now the information about how long it takes to actually reach here. So we can use that information and plug it into information, and then we can go to the vertical part of the motion. And what is what we're trying to find? We're trying to find the delta y. Well, actually, we're trying to find, the delta y. If we think about this, we're asking how far below it's hitting, right? I think that was the question. So it's kind of going to hit below. That's given in the wording. It could hit above. It's going to be a matter of sign. Now we can use delta y, and we will then convert that information to the actual answer. It's going to be important, but we'll get to that. So we're going to ask about delta y at time equals 3.3 seconds. And we have no information about the final velocity. So we can use the equation where we're missing final velocity, and we're going to try to find information on the displacement. And of course, we can use that basically saying y is equal to y sub 0 plus v sub 0 y t plus a sub y t squared divided by 2. Now we know the time, we know the acceleration, we know the initial velocity. So what we can do over here is say that y minus y sub 0, which of course this is delta y, displacement, is equal to v sub 0 y times t plus a sub y, which is minus, well, let's actually replace already with the numbers. We don't know this, but we know that v sub 0 y is 12.9, so 12.9 times 3.3 seconds, so 3.3 seconds, plus acceleration in the y direction is minus 10, time is 3.3 times square, 3.3 squared divided by 2, so that's going to be the delta y. It's equal to 12.9 times 3.3. Let's check on the calculator. So if we use the calculator, 12.9 times 3.3 is about 42.6 plus minus 10 over 2 is minus 5 times 3.3 squared. This is close to 11ish. This is 54.5, but negative. Do not forget the sign. So it's minus 54.5 or negative 50.45. 42.6 plus minus is going to be obviously a subtraction, and this is actually 11.9, but minus 11.9. And that's the answer to this question, that is minus 11.9 meters. Now let's make sense of this. Let's use this portion of the board. So we have the delta y, which is of course y minus y sub 0. It's actually minus 11.9. What does mean when displacement is smaller than 0? It is of course because the initial position is larger than the final position. So of course this is the case. So we can just, instead of saying, well, we say the displacement is negative, means the displacement is pointing downwards. So if the question was how far above or below its original level will the ball strike the opposite wall, we don't know if it's going to be above or below. We take the displacement, because the displacement, if the displacement was positive, the object will be hitting up, right? These are displacements that are positive because this is y sub 0, the same height as the building. But because the displacement is negative, we know that it's going to be pointing down, right? So how far below? It's actually 11.9 meters without the sign. The sign is just telling us, because it's in one dimension, it's just telling us the direction upon which the displacement is happening. So plus 11.9, it goes up. Minus 11.9, it's going down. And so in 15 meters, you are capable of raising and lowering all the way up to 11.9 meters. So the answer to the question is how far below or above. The answer is it is below, and it's below close to 12 meters, 11.9 meters. So last problem to check. So we have a child on a wagon, it's problem number 9, and he's moving with constant velocity, right? So we could just say that the cart has a constant velocity and it's moving sideways. So it's constant velocity, so we know the acceleration is 0, right? It's moving with constant velocity, and it throws an apple, and we're asked a certain amount of time later, is the apple going to be behind, it's going to be ahead, or is it going to be again in the hand of the child? So is it going up and down, and it falls in the hand, while this guy is with the child is going right forward. So let's do this. Remember, motion starts always from frame of reference, which is the point of view. Let's describe this from the point of view of the child. So from the point of view of the child himself, is he moving? Right? From the frame of the child, is the child moving? No, the child is just stationary. So the fact that the object is moving with constant velocity, the cart, it means that there's no acceleration. So it means what we call inertial frames of reference. So in this frame of reference, then all the laws of physics should be the same. So from his point of view, he's not moving. So actually, he doesn't have any velocity. What about the apple? With respect to the kid, the apple is not moving horizontally, right? From the point of view of the kid, if we make the description of the apple doesn't have any initial horizontal velocity, because the kid doesn't have any initial velocity. So what's going to happen is that the apple has an initial vertical velocity, which is obviously not going to be 0, and there is a gravitational acceleration, which is obviously minus 10, which is g, but there is no acceleration horizontally. So the final velocity is obviously going to be also 0, and the final velocity is going to be just simply the opposite of the one, because it goes up and down. We've seen this before, it's symmetric, but that's not that relevant. What matters now is the position of the object. If that is the case, there is no change in the x position. We saw that. It's just simply a vertical throw. So when I throw an object, it just falls in my hand because I'm not moving. And if I'm walking and I throw the object falls in my hand as well. Why? Because the object is thrown vertically with respect to me, but I'm also walking. So with respect to someone outside, I have a constant velocity, but that constant velocity is going to be also the same of the object. So in that case, we can see that indeed, because there's only vertical component of the motion with respect to the child, we can ignore the horizontal. If there is no horizontal, it's just free fall. We never wonder why when I throw an apple from the top of a building, the apple just falls down. It necessarily falls down. Why would I expect it to fall ahead or behind the building? That would be kind of crazy. We consider that when we are in motion, because we are just forgetting that the motion that we have, the apple is also having. And usually in real world, if you open the window of your car, when the car is in motion and throw an object, the object falls behind. But that's just because there is air friction. And that is a very important concept. And it was Galileo who realized that friction was messing up all the conceptual framework that previous people from Aristotelian physics we had. And once he was capable of imagining a world without air friction, and in fact he did some experiments that tried to replicate as close as possible like, as one could get of vacuum at that time, he actually saw that indeed the objects have certain velocity. We'll see that's at the very essence of, at the root of the first law of Newton, which is the law of inertia, which was first initiated by Galileo, and in fact we can see it centuries before Galileo already in the scholastic natural philosophers with the concept of, for instance, of impetus of Jan Buridan. So the idea here again is, if you think, set your frame of reference. If your frame of reference is yourself, you're not moving, you're just dropping the apple up and down. If it's up and down, it's the same as being on top of a building. The apple is going to be falling down. And if you see it from the point of view of someone outside, the apple is moving with horizontal velocity, which is the velocity of the car, and vertical. And so, of course, it's going to do a parabola. But it's going to fall exactly at the same place that this object, because this object is moving with a horizontal velocity the same as the apple. So two objects moving with the same velocity, the fact that one has vertical component and the other one does not, it doesn't matter. Both have the same horizontal description of the motion. Both are going to be exactly at the same position horizontally at the same time. Vertically, of course not. The object is going to raise and lower, whereas the kid is going always flat. But that's just because, again, we can split motion into horizontal and vertical components.